right, good evening, everyone. Thank you all so much for your interest and enthusiasm for this year's Marty Sklar My Last Lecture. My name is Sarah Lee, and I am the Vice President of the Alumni Scholars Club. We are happy to uphold this annual tradition of honoring our outstanding professors through UCLA's biggest student-nominated faculty award. Before we begin, though, I would like to quickly explain how this tradition began and what it really means. So back in 1955, UCLA honored 6 renowned Bruins, such as Coach John Wooden, through a series of lectures called My Last Lecture, inspired by Professor Randy Pouch's memoir. Back in 2010, the Alumni Scholars Club revived the celebration in partnership with a former alumni scholar and Disney legend, Marty Sklar. Each year, we allow students from all over campus to vote for their favorite professors who inspire, motivate, and challenge them. During the ceremony, the winning professor goes on to share his passion or wisdom through answering the question, if this was your last lecture on Earth, what would you say? Although our current circumstances prevent us from celebrating together in person, I am super glad we could all meet in this virtual space tonight. The journey of getting here took a drastic turn when we found out that spring quarter would transition to online learning, but we were able to push forward and still host the event with the help of many special individuals. So I would like to take the time to start off by thanking the Alumni Association, without whom this event would not have been possible. The Alumni Association provides staff and financial support to the Alumni Scholars Club and allows us to create programming that reaches beyond the campus community. I would like to thank my supervisors, George Brown and Anna Hamilton, for guiding me through this process, and also want to give a special shout out to Gloria Ko, whose Zoom webinar we're using tonight. Also, I want to thank the Alumni Scholars Club Executive Board for rallying together to spread the word about this event. And last but not least, my committee members, Kate Santoso, Grace Yang, Katrina Kan, and Amy Kumar. Thank you guys so much for being such supportive teammates and spending the last 2 quarters with me, taping flyers all over campus and counting up nearly 2,000 votes. Now, I've said a lot, so let me go on to introduce the star of the night. Our 2020 Marty Sklar My Last Lecture Award recipient hails from Finland and has pursued his love for mathematics and philosophy through an extensive journey that brought him westward to UCLA. After completing his PhD in number theory in 2015, he became an instructor at UCLA through the Life Sciences Core Education Department. For the last 3 years, he has been teaching the Mathematics for Life Scientists series to our undergraduates who often leave the course with a feeling of appreciation for his engaging teaching style and fond memories of Flippy and Puffers. Without any further ado, please welcome Dr. Jukka Keranen to our virtual stage.
Thank you so much, Sarah, for that introduction. Let me just go ahead and share my slides here with all of you. And here we go. Welcome everybody to my last lecture. Our topic tonight will be symmetry, and I will be an instructor. I'm Jukka, and for your learning outcomes tonight, we will have, well, just have fun with it. First, I want to thank the UCLA Alumni Scholars Club for this amazing honor. When my friend Will Conley won this award 4 years ago, I thought to myself, man, that is a very special thing. But I'll be honest, I also thought to myself right away, man, I would love to win that myself one day. Not that I thought it was ever going to happen. So truly, from the bottom of my heart, thank you so much. This means a world to me. I want to thank the faculty and staff of the Life Sciences Core Department. The LS Core has been my academic home for the past 3 years now, and I could not be happier. I love all of my colleagues there. I love everybody I work with. And honestly, one could not hope for a better, one couldn't possibly imagine a better, more supportive, more nurturing work environment. Thank you so much, all of you. I hope that a lot of you are hearing this tonight. I love you all. I look forward to working with you for a long time to come. Now, the reason I'm talking to you tonight is, of course, LS30, Mathematics for Life Scientists. Now, in a minute, I will tell you a little bit about what LS30 is, but I want to begin by thanking everybody who was involved in developing this course. First and foremost, of course, I want to thank Alan Garfinkel for creating such a beautiful course, and of course, I want to thank him for giving me a chance to teach it. I want to thank Jane Shevtsov for being such a wonderful colleague every day. And I want to thank Will Connolly for helping make LS30 the amazing success that it is. I want to thank all my past TAs. Now, you're the professor, you come to class, you do your best, you deliver the content best you can, but I'm full aware that a lot of the actual learning happens when the students go to the TAs, when they go to the office hours, when they go to a TA section. So really, I want to thank all my past TAs for all their hard work and dedication. I want to thank also all my past LAs. Now, I'm guessing that most of you probably know what an LA is, but just in case some of you don't, let me quickly explain what LAs are. LA stands for a learning assistant. These are undergraduate students who work, if you will, as assistant TAs. So they are students who took the course, really enjoyed it, and decided that they want to come back and help their peers succeed in this course. LS30 has a very significant coding component, and I will explain more about that in a minute. And so in fact, the weekly TA sections are really coding labs. And so the LAs come to these weekly coding labs, and they work alongside the TAs and help the students work on their coding assignments. Quarter after quarter, our students tell us what an absolutely vital, amazing resource the LAs are. So thank you, all my past LAs. We could not do it without you. And of course, thank you to all my past students. Make no mistake, you are the reason why I have the best job in the world, the absolute best job in the world. Every day, I am so inspired to see how hard you are all working. I'm inspired to see how dedicated you are. I'm inspired to see your amazing attitude towards learning. Nothing could make me happier than knowing that, at least in some small way, I have been able to help you in your journey here at UCLA. And finally, most especially, I want to thank all of you for all the encouragement, for all the kind words that you have sent my way this past year. And of course, I want to thank you for this amazing award. Once again, from the bottom of my heart, thank you so much. And finally, of course, I must mention my two little classroom assistants. Yes, they are penguin pals, but really they are more than that, they are penguin mates. Please say hi to Flippy and Puffers. There you go. Flippy and Puffers say hi back to all of you. Welcome to my last lecture. Now, many of you have met Flippy and Puffers before, but if you haven't, let me just quickly explain. Like I said, Flippy and Puffers are my little classroom assistants. They come to every lecture, they come to most office hours, and they are there to provide moral support for everybody involved, the students as well as the instructor. And you notice here, of course, Flippy and Puffers are staying safe, wearing their scarves that one of my students was nice enough to make for them. And now you notice also, they are not wearing their face masks, or should I say their peak masks. But I assure you that if we need to leave the penguin hut here, they certainly will wear their masks, and I hope that you will too. Let me then tell you a few words about what LS30, Mathematics for Life Scientists, is. In fact, let me tell you what we are doing here as a civilization, right? The basic goal of theoretical science is to understand the ways things change in the world. We find ourselves in a very dynamic, ever-changing universe. It's not a static universe. And so as rational beings, in a way, the fundamental task that we find ourselves facing is to try and understand all the ways in which things are changing in the world. But not only understand, Also, we would like to be able to control them, at least to some extent. So the basic goal of applied science then, I suppose, will be to control the ways things change in the world. That is to say, we would like to build roads, buildings, develop medicines, and so on. And it turns out that one of the most important tools for doing all of that are what are called differential equation models of dynamical systems. So you may not know what all of those words mean. So let me just very quickly tell you what we are talking about here. First, well, a dynamical system is really just any collection of interacting things in the world, interacting quantities. For example, they might be the numbers of susceptible, infected, and recovered people, let's say in the state of California. So I promised myself that I would mention the thing, we all know what I mean, only once tonight. So this is the one time we will mention COVID-19, and then we are done. So this would be a very important dynamical system for us to understand. And the way we can come to understand systems like this is that we study differential equation models of systems like that. So what's a differential equation? Well, really, it's just it's a mathematical representation of the rate of change of these various quantities. So for example, this might be a differential equation model of the dynamical system where we are tracking the numbers of susceptible, infected, and recovered people in the state of California, let's say. So as you have guessed, the letter S stands for the number of susceptible people, the letter I stands for the number of infected people, and the letter R stands for the number of recovered people. Now, if you look on the left-hand side of these three equations, you see those letters with a little prime on them, S prime, I prime, and R prime. That just is the mathematical way of saying the rate of change of. So these are three equations that are meant to represent the rate of change of S, the rate of change of I, and the rate of change of R. And on the right-hand side of these equations, you see some algebraic expressions involving those three quantities, S, I, and R. I'm not really going to get into the details of what these equations are saying, but let me just say this. Right now, all over the world, scientists are using models just like this in an effort to understand the future course of the pandemic. This is a simple example, but fundamentally, this is the kind of thing they are working with. And so in LS30, our students learn how to predict the long-term behavior of dynamical systems by analyzing their models. And they do that through calculus, linear algebra, and numerical simulation. LS30A focuses more on calculus, LS30B more on linear algebra. But throughout the course, we put a real big emphasis on numerical simulation. See, here's the thing. These amazing mathematical ideas, the concepts of calculus and linear algebra, they give us amazing tools for analyzing models of dynamical systems. And yet, oftentimes, they don't really allow us to do exact calculations into the future. And that's where numerical simulations come in. That's where you find some set of current values for these quantities S, I, and R. You plug them into your model, you run a simulation of your model in a computer, and that's how you get these predictions about what might happen in the future. Oftentimes, that's the only thing we can do. So that's why we put so much emphasis on numerical simulation and using computers, like I said, in our course. And again, this is exactly the kind of thing that scientists world over are doing right now in an effort to discover ways that we might slow down the spread of the pandemic. In short, trying to make the world a better place for all of us. Tonight, though, I want to go a little bit beyond LS30. So there is a theme that is just beneath the surface in LS30. symmetry. You know, symmetry is one of those great unifying themes in all of science. And I dare say, in all of human civilization. In fact, one day, I hope to develop and teach LS30C, symmetry in the living world. And so I thought that tonight, it might be kind of fun to say a few general things about symmetry. So here's what I'm going to do. I am first going to just briefly indicate the importance of symmetry in science. I will then try to give you some sense of how mathematicians think about symmetry. I will tell you a few personal anecdotes organized by this theme of symmetry, and of course, throughout, I will show you some nice pictures. So sit back, relax, let's talk about symmetry. Let's begin by talking about symmetries in the physical world. Now, this lecture is going to have 3 parts. Here in the first part, again, we will talk about symmetries in the physical world. In the second part, we will talk about symmetries in mathematics. And in the final part, well, you'll see. We will try to apply the symmetry concept a little bit beyond science as such. I think you'll like it, so stay tuned. Now, when it comes to the physical world, it's really symmetries all the way down. It's not turtles, it turns out it's symmetries. Symmetry is found at all levels of magnitude in the physical universe. It's found in astronomical structures like galaxies, solar systems, and planets. It is found in the morphology of animals and plants. It's found in crystals and molecules, but really more than that, much more deeply than that, it is found in elementary particles and indeed in the very laws of nature. And I will tell you just a little bit about that in a moment. Now, of course, you all know that symmetry is also a pervasive device used in art, perhaps precisely because it is so pervasive in the world around us. Of course, symmetry permeates visual arts and architecture, but actually you will find a lot of symmetries also in music and literature. Now, you might find the final 2 points a little bit perplexing right now. I'm not going to say more about it just yet. Rather, we are first going to do the lecture, and I'm going to give you some of the tools that you're going to need to think about symmetries in all of these domains of activity, including music and literature. So I'm hoping that by the time we are done, you will be able to think of examples of symmetries in music and literature as well. So the first main thing I want to get across tonight is that there are many different types of symmetries. I know you're already all thinking, oh, there, that's a symmetry, right? Well, actually, there's so much more to it than that. So we will begin by identifying a number of different types of symmetries. Let's look at some examples. Of course, we are all very familiar with reflectional symmetry. To start with, human faces exhibit a high degree of reflectional symmetry. So I picked an example here. That, of course, is the extremely talented actor, Scarlett Johansson. And she is truly one of the great actors working currently. But today, she is here in our virtual space because of the high degree of symmetry of her face. So you have probably seen this little fun exercise before somewhere online. And so what they do, right, is that they take the face of some celebrity. And then by using the magic of computer graphics, they split it right down the middle. And they take the left half and reflect it. Then they take the right half, reflect that as well. And now you have 3 faces, the original and the left symmetry face and the right symmetry face, like you see here. And usually what happens, if you look around on the net, is that these reflected faces, these artificially created images, are frightening. Most people just don't translate that well when you reflect them like this. But here, and this is the reason why I picked ScarJo out of all the possibilities, it is quite remarkable how incredibly well she reflects. So if you look at the left symmetry and the right symmetry faces, it's basically the same face as the actual person's face. That is just an uncannily high degree of symmetry. Of course, you will find reflectional symmetry often in art and architecture. So here's one especially famous example of it. This is the Palace of Alhambra in Granada, Spain, built in the 13th century during the Moorish rule of what is now Spain. In particular, this is the Court of the Myrtles. Myrtles would be those green plants, those green bushes that you see on either side of the reflecting pool. So here in the Court of the Myrtles, in particular in that set of arches, we see reflectional symmetry twice over. So first, there is the reflectional symmetry from left to right. So if you split the big arch right down the middle, you can see that the left and the right sides are mirror images of each other. You can reflect one on the other and it will look the same. So you have that vertical axis of symmetry. But here, the architects were more inventive than that, and they created another axis of symmetry. By building the reflecting pool, we now also have a reflectional symmetry in the horizontal plane. And in this case, one of the two symmetric things is literally a reflection. Very clever. But that's not the only kind of symmetry. So this is the first thing I'm trying to tell you tonight. You may have had the idea that when we say symmetry, we only mean this, that we only mean reflectional symmetry. Actually, there's much more to it than that. So here's our second type of physical symmetry for tonight, rotational symmetry. So plants often exhibit rotational symmetry. Let's take a look at this beautiful tiger lily here. So you see it's got six petals there. 3 are sort of a little bit bigger than the other 3. And so what I can do here is that I can, if you like, I can grab it by the stem and I can rotate the flower. And if I rotate it through 120 degrees, I can go clockwise or counterclockwise, doesn't matter. If I rotate through 120 degrees, let's say counterclockwise, it will look exactly the way it looked before the rotation. I can keep rotating through another 120 degrees and it will look the same again. And of course, if I rotate one more time, I will have rotated through 360 degrees and then we are back exactly where we started. So this tiger lily flower has a, if you like, threefold rotational symmetry. It looks the same after you have rotated through 120 or 240 or indeed 360 degrees. Rotational symmetries also occur often at the molecular level. Many molecules and other molecular scale structures exhibit rotational symmetry. Here on the left, I'm showing you a picture of ferrioxalate. Well, it's a trivalent anion. It's more specifically a transition metal complex with an iron atom at the coordination center. That's the blue thing in the middle. And with 3 ligands, if you like, the plates around it. The plates are bidentate oxalate ions. Here, red are oxygen and black are, of course, carbon. But if you don't know what any of that meant, don't worry about it. Ferrioxalate, who cares? Let's just look at it. So you can see that that complex, again, has this threefold rotational symmetry. I can rotate it through 120 degrees, let's say counterclockwise, and it will look exactly the same as it did before the rotation. I can rotate it through another 120 degrees, it will still look the same. And if I rotate through one more 120 degrees, I will have come back to where I started. That is to say, now all the atoms are literally where they started out. And there on the right, I'm showing you a salt of this complex that happens to be a potassium ferrioxalate. I picked it just simply because I thought it looked kind of pretty. certainly more interesting than ferry oxalate by itself. And I don't suppose I can really get through a lecture on symmetry without showing at least one snowflake. So here you go. Here is your one snowflake. Now, what's interesting about the symmetry of snowflakes is that this is a case where we cross scales of magnitude. For you see the six-fold symmetry, there you go, the hexagonal symmetry of the snowflake is due to the hexagonal symmetry of the ice crystal, right? So when a snowflake begins to form, at the very beginning, it's just an ice crystal with 6 corners. And at each of those 6 corners, these arms begin to grow independently. And no, the symmetry isn't perfect, but nevertheless, it's often pretty near to being perfect, and in any case, extremely beautiful. I'm actually going to come back to this example a little bit later. One final type of symmetry I want to talk about tonight, translational symmetry. So I bet that this is the one that you would have had the hardest time thinking of on your own. A lot of you, well, of course, all of you have thought about reflectional symmetries before. Probably many of you have thought about rotational symmetries, but maybe not so many of you have thought about translational symmetries. So to illustrate this in art and architecture first, let's go back to the Alhambra. Let's go back to the Court of the Myrtles. So this set of arches will be our illustration, our first illustration of translational symmetry. So here's what I'm saying. Let's focus, for example, on the leftmost little arch, right? So you see, I can now grab that little arch. Yeah, there we go. I grabbed it. And I can move it one step to the right. And it looks exactly the same. I can move it another step to the right, still looks the same. Now, of course, in the middle, because the arch is larger, the symmetry is broken. But then beyond that, I could continue to translate my little arch to the right, and it would look like what it was. So this is what translational symmetry is. Let me give you another couple of illustrations again from Alhambra. So Alhambra is very famous for its tiles, for its decorative tiles. So here's just a couple of them. If you look at the one on the left first, you will notice that I could take any, let's say first horizontal row, right? Fixate your eyes on one of the horizontal rows. I can take that horizontal row and I can move it up 2 steps. And after I have done that, the pattern looks exactly the same as it did before. That's a translational symmetry. But now, as it happens, there's a lot more symmetry here. Now fixate your eyes on any vertical column. I can take that column and I can move it to the right or to the left, doesn't matter. Let's say right. I can move it to the right by 2 steps. And again, the pattern will look exactly the same as it did before the translation. Another translational symmetry. And actually there's even more, for you see, you can also translate diagonally. So I will leave it for you to see if you can see that maybe later on. And on the right, you see another pattern, another tile that has translational symmetries. And again, I will leave it for you to look at that at your leisure. Of course, often in art and architecture, these different types of symmetries all occur at once. So here's a larger sampling of tiles from Alhambra. And I think that if you look closely enough, you're going to be able to find many tiles that have at least 2 of these 3 different types of symmetries. And I think that you can find some ones that have all 3. So again, I will leave that as a little homework exercise for you. In any case, beautiful to look at, absolutely beautiful. Now, so far, we have looked at symmetries of physical objects. You know, we have looked at actual symmetries of shape. But actually, that's a very superficial way, right? very superficial way of thinking about symmetry. Actually, symmetry in the physical world goes so much deeper than that. And I'm now going to try to tell you in just a very, very brief way what that looks like. So let's talk about laws of nature. So I bet that many of you have heard of conservation laws in physics. In an isolated system, the total amount of some particular physical quantity must remain constant over time. Okay, that's the general form of a conservation law in physics. So for example, we have conservation laws for energy, for momentum, for angular momentum, and also also for electric charge, and just for fun, for something called isospin. If you don't know what that is, don't worry about it. If you do know what it is, good for you. All right, so what is the connection between symmetries and these conservation laws? Well, actually, the connection is complete. As it turns out, all conservation laws in physics come from symmetries. So really, it goes all the way down to the fundamental structure of the universe. So this is a result due to a German mathematician called Emmy Noether. In 1915, she wrote down a mathematical theorem and proved it that, obviously, speaking very roughly, says the following. Whenever a system has a conserved quantity, that system has a corresponding symmetry. All right, so let me be clear about something here. When we say symmetry in Noether's theorem, we do not mean actual symmetry of shape, right? So now we are going to, for the next few minutes, talk about symmetries in a little bit more abstract kind of way. So what symmetry means in this context is the following. You have your physical system. That physical system is symmetrical or has a symmetry with respect to an operation we might perform on it, like rotation or translation, if it behaves the same after that operation as it did before. So for example, energy is conserved in a system precisely when the behavior of that system does not change if we translate that system in time. Momentum is conserved in a system if the behavior of that system does not change if we translate that system in space. And finally, angular momentum is conserved in a system if the behavior of that system does not change when we rotate that system in space. So to put this very roughly, one more way is that conservation of energy happens when the system doesn't care where we put it in time. Conservation of momentum happens when the system doesn't care where we put it in space, and conservation of angular momentum happens when the system doesn't care how we orient it in space. And just for fun, again, if you know what I'm talking about, good for you. The conservation of electric charge corresponds to the U1 gauge transformation symmetry. Conservation of electric charge is ultimately related to the fact that the global gauge group of PH.D is U1. If you knew what that meant, good for you. If you didn't, don't worry about it. All I'm saying is symmetries in this more abstract sense, that the behavior of the system does not change when we perform an operation on it. Symmetries in that sense are what give rise to conservation laws in physics. And as you know, conservation laws are in a lot of ways the most fundamental principles of physics. They are the rock bottom laws of physics. So I think that that's a pretty fascinating thing that Emmy Noether discovered for us. And so let me take this occasion to talk about the person behind the theorem for just one moment. Again, Emmy Noether was a German mathematician, born 1882, died 1935. She made fundamental contributions to many areas of mathematics, most significantly perhaps to something called abstract algebra. In particular, she focused our attention on what are now called Noetherian rings. Now, I'm not going to give you a mini lecture on commutative algebra here. Here's the thing. Noetherian rings, in a lot of ways, are the right ones to look at when you want to build an interesting mathematical theory. They are, in some sense, the ones that are general enough and yet not too general to permit an interesting theory to be developed. She also made fundamental contributions to topology and, of course, as we just saw, to physics. And one indication of her incredible standing in the mathematics profession is that she gave a plenary address at the 1932 International Congress of Mathematicians. ICM is the biggest global mathematics event. It takes place every 4 years. And in fact, this is the place where they give out those Fields medals that you may have heard of, so to speak, the quote unquote Nobel Prizes in mathematics. So she gave the large audience a large audience lecture at the 1932 International Congress for Mathematicians. She was a faculty member at Göttingen University from about 1915 until 1933. Yes, I think that a lot of you can guess the significance of these years, so we'll come to that in a minute. But throughout her time at Göttingen, she was very well liked instructor, keeping perhaps somewhat in the theme of tonight. She was highly supportive of her many students, and she was very nurturing and always put her students' interests ahead of her own. And of course, once again, she was also one of the absolute giants of mathematics in the first half of the century. And for all that, you guessed it, she was expelled from her position at Göttingen by the Nazis. Happily, she was able to come to the US, and she joined the faculty at Bryn Mawr in 1933. However, unfortunately, in her second year at Bryn Mawr, she had to undergo a surgical procedure, and she died from the complications of the procedure soon thereafter. In any case, she's an absolutely wonderful figure in the history of mathematics, and she is somebody that the public needs to know much better than it does now. Emmy Noether is one of my personal heroes. I love her style of mathematical thinking, and I'm very happy that I had this chance to mention her tonight. All right, so that is the first of the 3 parts of our little lecture on symmetry tonight. Here in the second part, again, you will remember, we will now look at symmetries in mathematics. In fact, there's a kind of a nice segue here. So some of you who may be in the know might say that, well, you know, that was nice, you know, little few pictures and, you know, mention of Noether's theorem, but still really a very superficial introduction to symmetry in the natural sciences. For you see, symmetry and study of symmetries in chemistry, in physics, goes so much deeper than just those mere symmetries of shape. But the thing is that I'm not yet in a position to explain to you how that all comes about. Because of course, this is going to be about applications of mathematics to those areas. So before I can even say the words, I will have to tell you just a little bit about how mathematicians think about symmetries. So let's look at, for a little bit, symmetries in mathematics. So first of all, I guess that a symmetry is often thought of as a pattern, right? So we might say here, when we look at this equilateral triangle, that there's a symmetry in the fact that if you take the vertical axis, the axis labeled 1, there's the pattern that what's on the left looks the same as what's on the right. Okay, so there is this structural pattern that the equilateral triangle has. But actually, it turns out that in mathematics, it is better to think of a symmetry as an operation that preserves a pattern. So for example, let's take the operation of reflecting about that axis labeled 1. When we do that, of course, we will switch A and C, and B will stay where it was. It's much more convenient to say that the symmetry is that operation of reflection that preserves the pattern. And so let me make a definition, well, sort of. I mean, it's not going to be a real mathematical definition, but at least this will help us focus our thoughts for the remainder. A symmetry of a structure, call it S, is going to be a function from that structure to itself that preserves all the patterns in that structure. Now, of course, that's still very vague. So I'm just going to say one word, and if you know what it means, good for you. If you don't worry about it. Automorphisms. That's probably the most general, useful way to think of symmetries. They are automorphisms of various types of structures. If you didn't understand what that meant, it doesn't matter. We are not going to need it for the remainder. So then, in the examples that we have looked at, we would now say that it's the reflections, the rotations, and the translations that are the symmetries. It's the operations, or if you like, the functions that we will now call the symmetries. So let me make my second main point for tonight. So remember, the first main point was there are many different types of symmetries, right? Reflectional, rotational, translational. That was the first main point. The second main point of tonight is this. If a structure has one symmetry, it will typically have many symmetries. Let's look at these two tiles from Alhambra as an illustration. So on the left, you notice you can have a rotational symmetry. So you can rotate through any multiple of 45 degrees. Again, counterclockwise, clockwise, doesn't matter. So you have the symmetry of rotating once through 45 degrees, but you also have the symmetry of rotating through 90 degrees and so on. So not just one symmetry, but many symmetries all at once. And of course, the same is true on the right. Again, I can translate this pattern by 2 spaces, but while I'm at it, I can translate it over 4 spaces all in one go, and that is another symmetry of that pattern. Again, one structure, many symmetries. This is such a fundamental idea that I want to explore this just a little bit more carefully. So I think it's fair to say that we are now somehow in the meaty middle part of today's discussion. Let's figure out the symmetries of equilateral triangle. So, of course, that's a triangle in which all the sides are of equal length, and therefore all angles are equal to 60 degrees, as you well know. And in this case, it's very easy to specify symmetry as a function. All we need to do is to say where the vertices A, B, and C are sent by this function. So let's tally them up. So here's the first symmetry. And I think this is the one that a lot of you might not have thought of. The very first symmetry of the equilateral triangle is do nothing. That's it. That's a symmetry, right? The pattern looks exactly the same as it did before the symmetry operation. After all, we have done nothing. A is still at A, B is at B, and C is at C. All right, now let's do the others. First of all, you can reflect about one of these 3 axes. You can reflect about the axis labeled 1. We switch A and C, B stays in place. We can reflect with respect to axis labeled 2. We switch A and B, C stays in place. And third, we can reflect with respect to axis labeled 3. We switch B and C, and A stays in place. And finally, we have those rotations. So we can rotate counterclockwise, let's say counterclockwise through 120 degrees, or 240 degrees, shown there. And that's actually it. Those are all the symmetries of the equilateral triangle. There are 6 of them, and that's all of them. How do I know that that's all of them? Well, here's one way of knowing. As you have realized now, in a symmetry of the equilateral triangle, basically I can take A and I can put it on any vertex I like. I can take B, I can put that any of the 2 remaining vertices, and then I can take C, and I will have to put it on the final 3rd remaining vertex. So how many choices did I have? 3 choices for A, 2 choices for B, and just 1 choice left for C. So 3 times 2 times 1 is 6. There you go. So there just aren't any more possibilities. These are all the symmetries of the equilateral triangle. And here's the point of all that. This is the 3rd, perhaps the final main point I want to make tonight. This set of 6 symmetries has the following remarkable properties. If you do any one of these symmetries and follow it by another, you will again get one of those 6. This is called composition of functions. So let me explain. Let's say I do rotate counterclockwise 120 degrees. Well, let's do it again. Rotate again through 120 degrees. Of course, those 2 rotations done back to back are the same thing as a single rotation through 240 degrees. There you go. That's what I mean. Now, of course, there are these more interesting cases. What if you do a translation, what if you do a reflection and a rotation? Well, you can work out that that is still just going to be one of those 6 operations that we already saw. So this is really all of them. The second remarkable property is that for each one of these symmetries, for each one of these functions, there is one that reverses its effect, right? If I rotate through 120 degrees to counterclockwise, how can I undo that effect? Well, of course, I can rotate through 240 degrees, which gets me right back to where I started. And indeed, you might notice that the rotate through 240 degrees is the same thing as, right, rotate clockwise through 120 degrees. And of course, for reflections, this is easier. If I reflect through any of those 3 axes, how can I undo that? Well, of course, I just reflect again. So for any one of these 6 symmetries, there's one that undoes the effect of the given one. And finally, for any 3 symmetries drawn from this group of 6, there's what you might recognize as the associative law. And now, here's the main thing. Any set with these 3 properties is a mathematical structure called a group. Let me say that word again, a group. This particular group is called D3. It's called the dihedral group D3. I will say a few words more about that in a minute. But first, let's think about group. Where have you seen groups before? Actually, all of you have groups before. Here's your favorite group, the whole numbers where the operation is addition. Let's think about this. If I take any 2 whole numbers, let's say 2 and 3, and if the composition in this case is just addition, okay, 2 plus 3 is 5, yes, I get another whole number. For any whole number, there's one that cancels it out, okay? 2 minus 2 is 0. Aha, notice, in this group, the group of whole numbers, the number 0 plays the same role as the symmetry do nothing plays in the group of symmetries of the regular, of the equilateral triangle. All right, and of course, all of you learned in school that the addition of numbers satisfies the associative property. So whole numbers with respect to addition are a group, just like the 6 symmetries of the equilateral triangle are a group. And therefore, we can now say that the study of symmetries is the same thing as study of these mathematical structures called groups. And it turns out that groups are absolutely pervasive in mathematics, absolutely pervasive. So first of all, there is a particular field of study called group theory, but it doesn't end there. Groups are applied throughout all subdisciplines of mathematics, and groups are everywhere in applications of mathematics. And therefore, it is not much of an exaggeration to say that symmetries are pervasive in mathematics. There you go. So in the first part of this lecture, I was telling you that symmetries are pervasive in the physical world. And now I'm telling you that symmetries are perhaps even more pervasive in the mathematical world. So just to reinforce what we have learned in the past few minutes, let me show you a couple of examples of groups of symmetries of geometric objects. So in fact, we have already seen 2 geometric objects whose symmetry group is a dihedral group. So we just saw that the equilateral triangle has a symmetry group consisting of 6 symmetries. And I just told you that the name of that group is D3. Well, actually, we can go back to the hexagon. It works exactly the same way for the hexagon. So the regular hexagon, the regular sixagon, has a symmetry group called D6, the dihedral group D6. And that group has, wanna guess, how many elements, how many symmetries? That group is going to have 12 symmetries in it. You have 6 rotations, where if you like, the final rotation is where you rotate all the way around 360 degrees. So I guess that the smallest rotation in this case would be through 60 degrees. You also have those reflections. In fact, you have 6 axes of reflection here, while for the triangle, you had 3 axes of reflection. All right. And so you can probably guess that I'm building up to a general pattern here. In fact, it is not too difficult to work out the group of symmetries of the general n-sided regular polygon. So you have just seen the 3-sided regular polygon. We skipped the 4-sided, that's a square. We have looked at the and the 5-sided, and we have looked at the 6-sided regular polygon. Well, guess what? It goes on in that same manner. The group of symmetries of the n-sided regular polygon is what is called the dihedral group Dn. How many elements, how many symmetries is it going to have? Wanna guess? Right, it's going to have 2 times n many symmetries in it. And in fact, it's not at all difficult to understand how it's going to work. So what I've given you here is called, well, it's called a presentation of this group, but don't worry about it. Let me just quickly indicate what's going on here. In order to understand how these dihedral groups work, you really just need 2 things. You first need the fundamental rotation. In this case, it's the sigma. The sigma represents the function that says rotate through 360 divided by n, right? So in our 2 examples, they were 120 and 60. And of course, again, when you rotate like that n many times, yes, you will end up coming back exactly to where you started. And in addition to that, you just need 1 reflection relative to one of those axes of symmetry. Why do you only need 1 reflection? See, that's the clever bit. You only need that 1 reflection because if you want to reflect with respect to any of the other axes, you just rotate first. There you go. So these are the symmetries of the n-sided regular polygon. Wonderful. So now we have some sense of what these groups of symmetries look like for geometrical objects. And for the same amount of money, let me just remind you that we have already seen 2 physical structures whose symmetry group is a dihedral group. So once again, ferrioxalate, there you go, on the left, ferrioxalate has symmetry group D3, and on the right, the snowflake has symmetry group D6. And yeah, it works it works almost exactly the same way that it works for these geometrical figures. So for example, for the ferrioxalate, right? So hopefully you can see pretty clearly from the picture that I can rotate this thing through 120 degrees, 240 degrees, and all the way back through 360 degrees, and I will get exactly what I had to begin with. Now, what you can't see quite so clearly from this picture, if you think of the ferrioxalate as a propeller, those three wings, those three blades are actually at an angle to the plane of the page. They're at an angle, just like the blades of a propeller would be. And so then, what's the other kind of symmetry here? How do I do the reflection? So if you took some chemistry, you might actually realize that there's a little thing here that you want to realize. I can't just reflect literally, for example, relative to the vertical axis. Because if I did that, what would I do? I would flip the chirality. I would flip the handedness of that complex. That is to say, I would go from one isomer to the other. And we don't want to do that. So actually, the other kind of symmetry in this case corresponds to rotating through 180 degrees around that plane, if you like, about through the plane of the page. You do that once, that switches the left and the right-hand sides, but it still looks exactly the same. And when you do it another time, you get exactly back to where you started. But again, here's my point. As a mathematical structure, the group of symmetries of the ferrioxalate is exactly the same as the group of symmetries of the equilateral triangle. All right, so I'm now going to segue perhaps to the a little bit more personal part of this lecture. So let me tell you a little about my first symmetry. So my first symmetry goes back to 1968. No, I wasn't born in 1968. I was close, but not quite so far back. What happened in 1968 is that Scientific American published this collection of essays about mathematics. So basically, this was a collection of articles about mathematics all the way back from the 40s, 50s, 60s, up to 1968. And so, in the early 90s, having grown up in Finland, I traveled to South Wales to attend high school at the Atlantic College. So I could talk about Atlantic College for a long time. Let me just say that it is an international high school founded in the 60s with the mission to improve international understanding. Of course, in the 60s, the superpowers were looking to destroy the world. So some forward-thinking people thought that, hey, maybe if we bring young people together from all corners of the world and they get to become friends, maybe that will improve international understanding and make us a little bit less likely to destroy ourselves with nuclear weapons. Great idea. And so I went there in the early 90s, and it was, of course, a huge transition for me personally. I had grown up in my little town in northern Finland, and I was now away from home for the first time. And if I may remind you, now this is the 90s, the very early 90s. So there's no such thing as the internet. Okay, there's no text messaging. So when I left my home, when I left my mom, that was a pretty big step for me. But of course, I was very excited. I was very excited to be at this amazing new place, meeting people from something like 100 and more different countries around the world. And so then, eventually school starts. And there's the first weekend when you are back to business. All the introductions have been done. Now it's just once again about you and the book and the homework assignment. So this is early Sunday morning, end of first week of school. So I have math homework. So I go down to the castle. Yes, the castle. As it turns out, my high school is housed in an honest to goodness medieval castle. I mean like seriously medieval. I mean like 12th century. So anyway, the library was in the castle, still is. And so I went there, 7 in the morning, it's foggy, it's misty, it's sort of raining something as it often is in South Wales. And so I'm sitting at a desk in an empty library and I work on my little math homework for a few minutes but it's early, you know, it's pretty early in the morning and it's a little chilly and I'm getting a little bit bored with continued fractions. So now I positioned myself strategically in the math section of the library. So of course, what I'm going to do is I get up and I start browsing through the shelf to see if there might be anything interesting there. And one of the very first books that I happen on is this, Mathematics in the Modern World. So first of all, just the title. I mean, so those folks back in the late 60s were not ashamed to give their book an impressive name that carries weight and consequence, Mathematics in the Modern World. So I was immediately fascinated by this. And in particular, I was fascinated by that picture. So what is that picture? Well, first of all, I think that we can all agree that there's quite a lot of symmetry to it, although maybe we are not quite sure, is it one of the 3 types of symmetry that we have seen so far? Maybe, maybe not. Now, I'm just going to say the words. What you're looking here is Poincaré's disk model of hyperbolic geometry. If you don't know what those words mean, don't worry about it. So for the sake of completeness, let me tell you that the group of symmetries of this thing is something called SU11. It's a big group. Again, if you don't know what that means, it doesn't matter. The point is, this was my first symmetry. When I was looking at this cover and when I was leafing through this thick book, I think that that might have been the moment when I decided one day I'm going to be a mathematician. So let me talk to you a little bit about another symmetry within mathematics that's very personal to me. Let's talk about symmetries of polynomials. So first of all, I'm hoping that that title, that topic, is sort of a little bit mysterious. I mean, symmetries of polynomials. I mean, polynomials a polynomial. I mean, how is there any symmetry to it? Well, that's the point. Let's make it visible. So of course, you all know the quadratic formula. If I give you any quadratic equation, you know, ax squared plus bx plus c equals 0, you know what to do. You know what to do. You know that you can find its solutions by using the quadratic formula. The solutions are given by, okay, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And usually that's 2 solutions, although if the square root is 0, then it's just 1 solution. Anyway, it works. It always works. And it turns out that a similar formula exists for polynomials of degrees 3 and 4. You can find them on the internet. They are more complicated, but they are in principle the same kind of thing. You take sums, you take differences, you take products, you take quotients, and you might have to take roots. Here we are taking a square root. For these others, you might have to take higher order roots, like cube roots, let's say, for the cubic equations. But anyway, it's the same basic business. You can write the solutions of any polynomial in degrees 3 and 4 by using the corresponding general formulas. Okay, and that's where we were around 1500, right? That's where mathematics had progressed in this area by the early 1500s. And of course, what mathematicians want to do next is, right, they want to find the corresponding formula for polynomials of degree 5 and 6 and 7 and higher, right? But they just couldn't do it. They could not find a general solution formula for polynomial equations of degree 5. And in fact, here is the amazing thing. For degrees 5 and higher, there is no such general formula. It doesn't exist. It can't be had. And so, why is that? So this is a topic covered by something called Galois theory. It's all about the group of symmetries of the solutions of the equation. Again, the symmetries of the solutions as a whole, as a group. And so it turns out that for polynomials of degree 5 and higher, this group of symmetries of the solutions is in some sense too complicated. Now, I'm not going to get into the technical details of what too complicated means in this case. Let me just say that what you want to do is you want to look at the group of symmetries and you want to look whether that group has a certain structural feature. When degree is 5 or greater, for some polynomials, you can do it. Some polynomials can be solved in this way, but many can't. And for the ones that can't, the group of symmetries of the solutions is in this technical sense too complicated. So in short, in order to understand why some polynomials can be solved by using these operations and others can't, you have to look at the symmetries of the polynomial. Let me give you just one example. Let's look at this degree 5 polynomial here. F of x is x to the power 5 minus x minus 1. It doesn't look all that bad, right? I mean, it seems like, one could imagine perhaps writing the solutions in terms of sums and differences and products and quotients and taking roots. I mean, why not? And here's the roots. Here they are. So what I'm doing here is I'm showing you the complex plane. If you've never seen it before, you know what? Don't worry about it. But if you have seen the complex numbers, then you know exactly what I'm saying here. These dots are the 5 solutions of that equation presented in the complex number plane. So you see that there's one real solution, it's an irrational number, and then there are 4 complex number solutions, properly complex number solutions. And now, it turns out that the group of symmetries of those 5 solutions is the group of all permutations of 5 things. In fact, you may know from your combinatorics course that that group has 120 symmetries. But the number of symmetries is not the point. So the trouble is that there are a lot of symmetries. The trouble is that as an algebraic structure, the group of these symmetries has it lacks a certain structural feature that it would have to have in order for us to be able to express those solutions by using those elementary operations. So in this case, the group of symmetries of these solutions is too complicated. And so these 5 solutions cannot be expressed by using sums, differences, products, quotients, and radicals. Radical just means the operation of taking roots of various orders. So there you go. That's your one example of a relatively simple looking polynomial whose symmetries are so complicated that we cannot express the roots, no matter how hard we tried, by using these elementary operations. And so this is, again, a topic called Galois theory, the study of the symmetries of polynomials. So I want to, again, take this occasion to highlight an instructor that I have had. So this fellow here is Richard Borcherds, born in 1959. He is, in fact, a professor of mathematics at UC Berkeley, one of our sister schools. He is one of the greatest mathematicians now living. He won the Fields Medal, again, if you remember the quote-unquote Nobel Prize for mathematics back in 1998. He won it for work involving something called moonshine, or even more romantically, monstrous moonshine. Sometimes mathematicians do give their work fun names. So he proved the so-called moonshine conjecture back in 1992. Now, I am certainly not going to explain to you in detail what the moonshine conjecture was. Let me just explain what the word means in this context. The word moonshine here means crazy, something incredible. What was so crazy were certain numerical coincidences that mathematicians discovered in the 70s and 80s. Numerical coincidences between quantities that really seemed to have nothing to do with each other. And explaining where these coincidences came from was the work that Richard Borchers finished. And here's what it is. The monster group is the symmetry group of the moonshine module. Of course, words that we are not going to understand tonight. But here's the point in English. Symmetries can help us to understand mysterious things, right? Let's go back to the mysterious sentence. What I'm saying is that many people, many other mathematicians, and Richard, building on their work, were able to identify a certain structure. That was the moonshine module. And they were able to look at the symmetry operations on that thing. And it turned out that this was the key to understanding those mysterious numerical coincidences that had been discovered earlier. Now, my personal connection with Borchers is that he taught the first class I took in Galois theory back in early 90s. Yes, back in the dim mists of history, back in the early 90s. Richard Borchers taught a course on Galois theory. This was back in Cambridge. And I hope that I have sufficiently impressed upon you that he is one of the truly great mathematicians of the age. But here's the point. He is an absolutely wonderful instructor, absolutely wonderful. His lectures were always well organized, well paced, very clear. And not only that, his homeworks were absolutely beautiful. As you know, the hardest thing in mathematics are proofs. Rather than going through complicated proofs in lectures, he broke them down into nice and easy sequences of homework problems, and so then we students could do the proofs ourselves. Absolutely wonderful. Love the guy. And so then, I guess that Richard Borchers features in this story for two reasons. First, because his actual groundbreaking work involves symmetries, but also because he taught me something about symmetries of polynomials back in the early 90s. And actually, my affiliation with Galois theory goes even beyond this. As my students know, I actually have a PhD not only in mathematics, but also in philosophy. And in my philosophy PhD thesis, I actually examined Galois theory. So here you go. I examined the shift from Abel's 1826 approach to the solvability of polynomial equations by radicals to Artin's 1940 approach. Okay, I'm not going to get into details, but here's basically what this was about. That amazing fact, right? That when the degree of the polynomial is 5 or greater, you can't have a general solution formula. That fact was first proven by a Norwegian mathematician called Abel in 1926. And then some years later, it was proven again by using very different tools by a French mathematician called Évariste Galois. And then Galois' sort of originally very complicated work was eventually cleaned up, and the first fully modern presentation of that work comes in Artin's 1940 book. And here's the point. Abel proves the theorem without knowing about groups, at least not using the structure of groups in any serious way. Whereas what Galois did is that he brought in full way the idea of group of symmetries and thinking about the structure of the group of symmetries into play. And that's the difference. And what I was trying to think about in my philosophical work was, well, what can we say philosophically about the difference between these two types of mathematical reasoning? By now, however, I am a mathematician, or at least I want to be a mathematician. There's a famous mathematician who wrote a book called I Am a Mathematician, and then another one, nearly equally famous mathematician, wrote a book called I Want to Be a Mathematician. I think you get the point. So I think I'm going to align myself here with Paul Halmos-Moore, that's the latter guy. I want to be a mathematician. So I want to be a number theorist. Number theorist is a person who studies symmetries of rational numbers. Let me try to explain just a tiny bit what I mean by that. That's looking at the group of symmetries of all polynomials with rational number coefficients. All right? So a few minutes ago, I talked about the symmetries of a single polynomial. Now imagine that that polynomial has rational number coefficients. Now take all polynomials like that. Of course, there's infinitely many of them. Now take all the solutions of all those polynomials with rational number coefficients. You add these in to the domain of rational numbers, and you get a new algebraic structure. It's called the algebraic closure of rational numbers. And what you can do is you can look at the group of symmetries of the algebraic closure of rational numbers. In other words, you can look at the group of symmetries of all polynomials with rational coefficients. It is, of course, an infinite group. It is an extremely complicated group. In some sense, we know almost nothing about it, but we are trying. All the number theory that there ever was, all the number theory that ever will be, is in some sense packaged in that single, incredibly complicated group of symmetries. It's called the absolute Galois group of the rational numbers. And that's what people like me are hoping to understand. And one person in particular made a huge leap forward in understanding that group back in the 90s. So when I was in college at Princeton, one of my professors there approved what is probably the most famous theorem in number theory, possibly the most famous theorem in all of mathematics. And here it is. Let's look at an equation. One final time for the night, let's look at an equation. By the way, you've been wonderful. Thank you for sticking with me. One final equation for the night. X to n plus y to n equals z to n. Well, let's think about this. Let's first make that exponent n equal to 2. Okay? X squared plus y squared equals z squared. Aha! Now we know what we're talking about. That's the Pythagorean theorem. That is the relationship satisfied by the sides and the hypotenuse of a right triangle. And here the point would be that there are lots of whole numbers that satisfy that relation. For example, 3 squared plus 4 squared equals 5 squared. 9 plus 16 is 25. So here's a question. One of the most famous, most fateful questions in history of mathematics. What if we make that exponent 3 or 4 or 5 or anything you like? Can you still find whole number solutions to that relationship? Can you still find triples of whole numbers x, y, and z such that x to the power n plus y to the power n equals z to the power n? Well, here's the famous theorem. You cannot. You cannot. So when n is greater than 2, a whole number, then the Fermat equation has no non-trivial whole number or even rational number solutions. Now, when I say non-trivial, of course, I can always stick in 0, 0, 0 or something, okay? But you can't have any solutions in rational numbers, never mind in whole numbers, to that equation when n is greater than 2. So this is the famous Fermat's last theorem. It was conjectured by a French mathematician, Pierre de Fermat, in 1637, and finally proven by Richard Taylor and Andrew Wiles in 1994. Notice that's 357 years later. So, sometimes in physics, problem might be open for like 10 years, 20 years, and 30 years, and it's a big deal. Well, guess what? In mathematics, the hard problems might be open for hundreds of years. This one was open for something like 3.5 centuries. Now, as some of you probably know, Pierre de Fermat claimed to have a proof of this result back in 1637. And that's the famous line, "This margin is too small to contain the proof." Okay. Now, by now, we are pretty confident that Fermat did not have a proof. See, he had a technique that was able to give the proof in certain special cases. And I think what probably happened is that he thought that the same technique would work in general, though now we know that it does not. And so then finally, the proof was finally completed by Andrew Wiles, that was the professor at Princeton, and his grad student, Richard Taylor. In fact, there's a lot more drama to this story, but it's well documented, and I will let you go and find it online. In short, after Wiles announced his result, an error was discovered, and he spent a year, more or less, trying to fix that error. And finally, he was able to do it with the help of his one-time grad student, Richard Taylor. So lots of drama, fun story, many books, many TV shows about it. You can go and find them online. But here's the point for tonight. Fermat's last theorem is a very deep fact about symmetries of numbers. Somewhere in this proof, which of course is a tremendous, incredible conceptual accomplishment, somewhere in this proof, Taylor and Wiles are able to give us just a little bit better understanding of what's happening with that so-called absolute Galois group of rational numbers, the group of all symmetries of all polynomials with rational coefficients. I hope you will look it up. It's a wonderful thing. And so my own work in number theory is sort of in the warm afterglow of the intellectual explosion that was the proof of Fermat's last theorem. I use many of the same ideas, many of the same concepts that Taylor and Wiles invented back in the 90s. And I really should mention something here. Like most works in mathematics, the proof of Fermat's last theorem was the work of many people, not just of these two people, but many more who had invented remarkable ideas before them and set the stage and laid the foundation for the proof of Taylor and Wiles. And one of those people who invented one of the absolute key components in the proof is our very own Harusa Hida. Hida is a professor at the math department here at UCLA, and he invented one of the key ideas needed in this proof in the mid-1980s. Hida himself, one of the absolute top mathematicians of his generation. All right, so there you go. Congratulations, you have made it through a little lecture on symmetry in the physical world and in the mathematical world. So just one final thing remains to say. What can we take away from this as human beings? For a minute, not as scientists, not as mathematicians, but as human beings. Let's think about asymmetric life. And I want to dedicate this final part of my presentation to a very special group of people, some of whom are here tonight, namely the class of 2020. Congratulations, UCLA class of 2020. You have done an amazing, wonderful thing. You are just about to conclude your work here at UCLA. Congratulations, you have a wonderful, wonderful future ahead of you. So with that in mind, let's think about how you could make the best of your future. So let's think about a symmetric life. What might that mean? Well, let's focus our attention on this beautiful symmetric object here. As it happens, that is something called E8. It's an exceptional Lie group. Doesn't matter what it is, it's a beautiful pattern with lots and lots of symmetry. Well, I'd like to think that that might be, in a way, a representation of a person's life when it's really symmetric. So you see, all of our lives have many dimensions. We are being pulled in many different directions. There are many demands placed on us and our energies. And I think that one key to a life worth living is to keep it in balance. So a symmetric life would be a balanced life, just like this object here, as you can see, is beautifully in balance. And not only that, it is very focused. So when I say keeping things in balance, yes, I do mean in part things like keeping a balance between work and play, family, love, and so on. And of course, balance is extremely important. But let's be honest. If you want to achieve something remarkable in your life, you are going to have to work hard. You have already achieved something remarkable in your life by completing your degree here at UCLA, and you worked very hard to do it, and you're rightly proud of it. And this is the perfect preparation for the next stage in your journey. You all want to accomplish remarkable things. And in order to do that, yes, you will want to maintain balance, but yes, also you do want to be very focused. Do not squander your energies. Keep them focused on what is important to you. Make your life meaningful to you by keeping it strongly focused, just like perhaps this picture here is strongly focused around its center. Also, I'd like to think that a symmetric life is one that is equitable. Treat others fairly. Do not put yourself above others. We are all penguins in this together, right? We are all equally penguins in this crazy game of life. Don't be proud. Don't be arrogant. Don't elevate yourself above others. But neither do let others push you down. We are all equally important as human beings. And that's what I mean when I say a symmetric life is an equitable life. It is a life that is fair and just towards your fellow men, perhaps I should say your fellow penguins. And I would like to think that a life with these features, a symmetric life that is balanced, focused, and equitable, is ultimately a beautiful life. Now, very difficult to give advice on how to live your life when, of course, one is so sorely lacking in wisdom in such matters oneself. But there is one thought that I have really enjoyed thinking about through the years. It's attributed to various people, perhaps to Salvador Dali, maybe Picasso. Whoever it is, here's the thought. Make your life a work of art. And maybe now I can say, make your life a symmetrical one. Live symmetrically. Some of you are lucky, some of you are fortunate enough to be able to make actual works of art. Write literature, write poetry, compose music, paint pictures. And that's beautiful, that's wonderful, you should go do it. But I think that all of us have the ability to make our lives a work of art. And tonight I'd like to suggest that one way to make that goal more concrete is to live symmetrically. Class of 2020, congratulations. Go out there and be amazing. I love you all. Thank you so much.
Thank you so much, Dr. Keranen, for such an engaging and insightful last lecture. And right now, I would like to end tonight's ceremony with a few words for Dr. Keranen and the brewing community. So on our RSVP form, we received about 426 unique messages of appreciation for Dr. Keranen. I spent an hour compiling all of these together and came up with 18 pages of anecdotes and thank yous. So browsing through these messages, I see that there is no one word to describe who Dr. Keranen is. Funny, engaging, caring, and understanding. Many students wrote that Dr. Keranen made them feel welcomed at UCLA and also told them to believe in themselves. One student in particular wrote in all caps, Dr. Keranen is the GOAT, aka greatest of all time. So I think this goes to show that he has positively impacted so many of his students' lives. Professors like Dr. Keranen are at the core of what makes our brewing community so strong, special, and a place that will be missed by class of 2020 as we leave campus this June. So as we are sitting in our homes miles away from each other, please give a virtual round of applause as I, on behalf of the Alumni Scholars Club and UCLA Alumni Association, present Dr. Jukka Keranen as the 2020 recipient of the Marty Sklar My Last Lecture. Congratulations, Dr. Keranen.
Well, thank you so much. This is just really wonderful. I truly want to thank all of you from the bottom of my heart. And once again, of course, I do want to thank all of my students. I love you. I love all of you, and I hope that you will all stay in touch. Now, earlier, I thanked a lot of the people who have helped me do my job. But there's one person I have not thanked yet, and that is my mother. My mother, too, is a teacher. And so I would like to dedicate this wonderful award to my mother. Hey, äiti, tää on sulle. Once again, thank you so much.